Kitchen Table Electronics, Advanced Topics for Lesson 5, Number 3, Complex Analysis of the RC Circuit. Okay, so let's go back to our high-pass filter with a capacitor in series with a resistor, and we measure the output voltage here. This is the input voltage here, and once again we're assuming they're sine waves so we can use our newly learned complex analysis. This circuit, of course, is just a voltage divider with the impedance of the capacitor being minus I over omega C as we just derived. And so writing the output voltage as the current through this resistor times this resistance in ratio to the applied voltage, which would be the current through this impedance times that impedance plus the current through this resistance times that resistance, we have the voltage divider equation giving that V out over V in is R over the sum of these impedances, which is R minus I over omega C, or alternatively omega RC divided by omega RC minus an almost invisible I. Okay, let's keep this expression here and let's do some calculations with it. One of the things we're interested in is the magnitude of V out divided by the magnitude of V in. This was what we calculated using our peak-to-peak measurement on the oscilloscope, so we're not worrying about the time variation now, just the peak voltage. And the magnitude of a complex number, as you know, is given by the complex number multiplied by its complex conjugate square rooted. So let's do that. We take this expression here, and here it is omega RC over omega RC minus I, that's this expression, and we multiply it by its complex conjugate, which is what? Just omega RC over omega RC plus I. So here's the complex conjugate. The top gives us omega squared R squared C squared. The bottom gives us omega squared R squared C squared, and then we have a plus omega RCI and a minus omega RCI which cancel, and then a minus I times a plus I, which is minus 1 times minus is plus 1. So here's the expression then for V out squared divided by V in squared. If we take the square root of this expression, omega RC over the square root of omega squared R squared C squared plus 1, we recover the expression that we presented without proof in lecture 5.3. What about the phase of V out with respect to V in? Remember in lesson 5.2 we looked at the phase of the output voltage with respect to the input voltage, and depending on where we were in terms of capacitor and resistive values and frequencies, we saw in one extreme where we were dominated by C that we had a 90-degree phase shift between the output and input voltage, and then in the limit where we were dominated by R, very high frequency limit, large capacitor value, we had V I and V, or V out and V in, almost perfectly in phase. So let's recall then that the phase of a complex number is given by the ratio of the imaginary to the real parts. And so here we go. Here was our expression for V out over V in, the minus invisible I here again. In order to separate this now, we have to rationalize it. And we're going to do that by multiplying this number by 1, i.e. omega RC plus I divided by omega RC plus I. And when we do this, we get omega squared R squared C squared plus I omega RC. And then on the bottom, we get omega squared R squared C squared. And then we have, once again, a plus omega RC times I and a minus omega RC times I, and then a minus I times a plus I, which is 1. We're interested in the ratio of the imaginary to the real parts, so the bottom cancels out when we take that ratio. And so here it is, the imaginary part, omega RC, divided by the real part, omega squared R squared C squared, and that is just 1 over omega RC. As you can see, when omega goes to infinity, then this quantity goes to 0, and the angle whose tangent is 0 is 0. So input and output are in phase. When this number goes to 0, the tangent becomes infinity, and that is the 90-degree phase shift that we get when the circuit is dominated by the capacitor. Finally, of course, we used a low-pass filter in which R appeared up here and C appeared down here. And again, I'm going to leave it to you to follow this analysis and derive the expression that was used in the lecture. Likewise, you can do the same thing for an RL circuit and derive the expression that was used in the appropriate lecture.